work. As he said, he'll be giving another talk tomorrow morning in the advanced RL session. So, yeah, it gives me great pleasure to announce our next speaker as well, who's another very good friend, Dr. Ndivhuo Makondo, who is based at IBM in Johannesburg. And his background, his undergrad and master's was at UCT, the University of Cape Town in South Africa. Then he did his PhD at Tokyo Institute of Technology, and during that time I had the honor of working with him. And after that as well, when he was at the CSIR in South Africa, say now he's at IBM, so he'll be talking about some of his work as well.
Thanks, Benji, for the introduction. So I'm sure you guys enjoyed the talk on reinforcement learning. So I'll be talking about how to apply supervised learning or supervised machine learning for robot control, for trying to solve some of the similar tasks. So the agenda of my talk looks as follows. I'll give a brief overview to robot control and give some motivation of why you want to use machine learning over some of the classical approaches. I'll give an overview of supervised learning approaches that have been applied over the past few years and some of the challenges faced when you're trying to collect data from physical robots for control. And lastly, I'll talk about some of the work being applied to address some of these issues. So when you think about robotics over the past few years, you probably think of an army of robots in some factory performing some simple repetitive tasks. This environment is fairly static and structured, so everything is designed around the robot, and the humans are sort of caged outside this environment. So this consists of fixed tasks, static objects, and there's very little variation of the tasks that the robots must perform. So this means that we only rely on human intuition and understanding of the environment and the robot to design control policies for the robots to perform the tasks. But recently, we've sort of witnessed a migration of these robots to unstructured environments and environments that are dynamic. For example, in agricultural robotics, and also drones for their delivery in remote areas. So this unstructured environments contains multiple tasks, moving objects, lots of variation of the tasks, which sort of motivated people to try and design systems that can learn and adapt to unknown situations. So before going into how you apply supervised machine learning, I'd like to give a brief overview for robot control. So the goal here is to control the joints of the robot arm in order to perform the task using its end effector. And the task is typically specified in this end effector space, which is intuitive to humans, but control takes place in the joint space. So this means we need functions to transform the task specification in the end effector space to the joint space for control. And there are typically two functions required. So there's the kinematics, which basically transforms the trajectories without the dynamics from the end effector space to the joint space. And also the dynamics, once you've got the trajectories in joint space, how do you predict the torques required to control the robot? So I'll mainly talk about dynamics control in this talk. So this is a widely used control architecture. So the assumption here is that you have a desired trajectory of your robot in joint space. So this is the movement of the joint angles over time. And you would like to use a model to predict the feed-forward command that you must apply to the robot. So this is the torque in order for the robot to track the desired trajectory. In practice, this model is not necessarily accurate. So you need to rely on a feedback controller in order to compensate for any errors and also stabilize the system. And typically this is a simple PID controller. Okay, so classically, there's a widely used model called a rigid body dynamics, which basically predicts the torque that must be applied. Actually, these vectors didn't come up properly. But anyway, so it's made up of different components that you must get from your robot. So you've got the initial matrix, which basically determines the torque that must be applied to get a desired acceleration around an axis. You have the Coriolis matrix. You have the frictional forces, the gravitational forces, and the task-based disturbances. So the success of this architecture relies on the accuracy of this model. Some of these parameters are actually difficult to get, such as the Coriolis matrix. There's no analytical formulation. There's also the frictional forces. So in practice, you're actually not going to get a very accurate model. So this model relies on human insights into physics to come up with mathematical models. And it typically requires your link dimensions, the joint configurations, and the link masses. They do work well under certain situations. When you have simple robot structures, low-speed reactive joints, and also stationary and structural environments, as I mentioned before. So, however, they do lead to modeling errors, as I mentioned before. And there are some nonlinear factors that you not incorporate into your model. And the model that you actually get is static. So if your robot changes over time due to degradation or wear and tear, your model doesn't actually adapt. And also, most of the modern robots are designed to be soft and compliant for human-robot collaboration, which adds complexity to the modeling problem. And also, since the type of humans, it's difficult to anticipate ahead of time how the human is going to behave. So that actually makes it difficult. So all these reasons led to researchers trying to use machine learning as opposed to the classical control approaches. And here the goal is that, or the hope is that, we're able to come up with more accurate models since we are learning them from robot sensor data. And also that we can incorporate all the nonlinear factors from the data. Also, since we're learning from data generated by the robot, the models can actually adapt to changes to the environment and the robot itself. And this could also lead to an autonomous operation of robots. So the control architecture is similar to the previous one that we've seen, except that now we have a model that's actually learning in real time instead of a predefined static model. So you have your desired trajectory, and you have a model that learns to predict commands to be applied to the robot and update itself over time. So in standard approaches, the model is randomly initialized. So it makes poor predictions in the beginning, but over time, also it has to rely on the feedback controller to kind of drive it around the task it's trying to perform. And eventually, over time, it learns to generalize over the task. So this leads to a supervised regression problem, where during training, the input is the actual trajectories of the robot, and the output is the command that was actually applied to the robot. And during testing, the input is the desired trajectory, and the output is the predicted torque. But in this case, training and testing happens in sequence, because given a desired trajectory, we like to predict the torque and learn from the data that the robot generated. But you cannot just apply any regression technique. So there's some criteria that you have to meet. So the first one is your model has to be able to learn online. So an incremental update is a parameter as new data comes in. And the reason is that robots are typically high-dimensional systems, so it's almost impossible to explore the entire state space to generate enough data to learn a global accurate model. And also, you want to be able to learn complex nonlinear functions, and your model needs to be able to update itself fast, and you also need to make quick predictions in real time. So research in this space over the past few years, was focused on how can we make non-parametric regression techniques fit this criteria. And one of the approaches used is Gaussian process regression, which you probably have heard of it from the Bayesian talks. But it's typically characterized by a mean function and a kernel function. So the standard Gaussian process, when it makes prediction, it has to invert a huge kernel function, meaning that its computational complexity grows with the number of samples. So next I'll talk about some of the techniques that have been applied to robotics to try and come up with fast model updates and predictions. So the first one is based on the idea of locally weighted learning. So the idea is that you want to approximate a complex nonlinear function using locally linear functions. And this will be able to make quick predictions using the linear functions. A simple example is that at each query point, you find the k nearest neighbors of that and you feed a linear function. Then you use that for prediction. So the more advanced techniques incrementally build local linear functions with their Gaussian kernel for computing distances. And at query time, you find a prediction for each linear model, and the output is a weighted linear sum of all the linear models. So the second approach is based on data specification. So the main idea is that instead of using all the data generated by the robot, you want to intelligently select a few samples that represent the entire data. That allows you to do quick predictions. And this is basically mainly applied for kernel techniques such as Gaussian processes. So you receive the data stream from the robot, and you select a few points. You actually have a fixed dictionary size that keeps all the data that you want to use for online learning. And you can actually use that size to determine how much computation you're able to do at each time. And the trick is how to select these points. So another approach is to use random selection. And this graph just shows prediction for Gaussian process using all the data points in red and using different sizes of the dictionary. You can see that even when using only 12 points, you're able to approximate the full Gaussian process. So far, we've assumed that you have data collected from the robot. But actually, in practice, it's actually very difficult to get data from the robot. And it's mainly because of the large state and action spaces. So this means that you need to perform trial and error for long periods of time in order to collect training data. And this is unsafe for robots. You can actually damage the robot from this. So next I'll talk about some of the work being done in trying to address these issues. So the common thing amongst this approach is the idea of using any available prior knowledge to accelerate your learning process. So the first one, which I've worked in, is if you have multiple robots that are trying to learn the same tasks, instead of each robot learning from scratch, can we reuse some of the data the robot generated in order to accelerate learning for new robots? The second approach is, instead of throwing away all the mathematical models that researchers have come up with, how can we combine them with supervised learning to accelerate learning? The third one is sim-to-real transfer. So learning simulation and adapt it to a real robot. The last one is meta-learning, where you learn variations of the same tasks and optimize to do well on a new related task. So transfer learning, so this is some of the work that I've done with Benjamin. So the idea is learn to adapt data between robots so that we can generate more data for the target robot. And this is particularly useful if you have a cheap robot that you can play around with, and you have a more expensive robot that you don't want to try and break. So you can generate a lot of data from this robot and learn to adapt the data. So this is a transfer. Actually, the graphs are not coming up properly. I guess they're the two different laptops. Basically, in transfer learning, you have two domains. So you have the source domain. This is a domain where you've collected a lot of data, or you're able to collect a lot of data. And you also have a target domain. So this is the domain where you have a new robot that is trying to learn its tasks. And in the source domain, this can either be a robot or a human, in the case of learning from demonstration. So the idea is how do you use source data to accelerate learning in the target domain. But in practice, the two robots could have different dimensions, which affects the dimensionality of the data. Could also have different distribution because of the different link masses. So for example, in order to track the trajectory using the PR2 robot, you may need a different top profile compared to the target robot. So the challenge here is, how do you learn to adapt the data in the source domain in order to be useful in the target domain? So the idea is learning a transfer model that you can use to adapt data to the target robot. So this is one way of doing it. So you have your source data, your source domain, you have a target domain. The idea is collecting a few samples of correspondences between the two domains that you can use to learn a mapping from one domain to the other. In this particular case, because the dimensions of the data set are different, so you usually perform dimensionality reduction process in order to match the dimensions and learn a mapping from the source to the target in this latent space. More recent work use approaches such as shared autoencoders or shared Gaussian process latent variable models. So I'll just show some videos showcasing the benefit of knowledge transfer, where we're actually transferring from a cheaper robot to a more expensive robot. So here you can see that starting from a randomly initialized robot model, the robot is just performing some random actions instead of tracking like a star trajectory that has been specified. And we can see that with knowledge transfer, even from the first trial, the robot is able to roughly track the star trajectory. So in this case, the robot has been given some prior knowledge, transferred from the source robot, and is able to use that to its benefit to start tracking the star trajectory properly. So another approach to try and accelerate learning is integrating domain knowledge. So in this particular case, you have a parametric model, for example, the RGBD model that I talked about in the beginning. You also have data on the right generated by the robot. The idea is, can you come up with a hybrid semi-parametric model that has these properties. And one simple example is using, so in this equation is equivalent to a Gaussian process centered at the RBD model, learning to absorb all the errors between the RBD model and the sampled point. And this has the ability that if your RBD model is accurate to begin with, the error term goes to 0. And when the robot moves to a different state space, then you rely on your RBD model to perform well. So the second approach is sim to real transfer. So the idea is to generate a bundle of data in simulation and then transfer that to the real robot. So the first direction is try to build high fidelity simulators. The second one is, even if you don't have a high fidelity simulator, use transfer learning to adapt your models learned in simulation to the real robot. So the last one is meta-learning, also referred to learning to learn. The main idea is to design models that can learn new skills or adapt to new environments rapidly with few training examples. And the idea is to extract information about the learning process itself to speed up learning for subsequent similar learning problems. So in this example, in this paper, you have variations of a task. For example, here you have a task of lifting Pringles, and then you have a variation of lifting a heavier material, which is a drill. And you have a meta-learner that extracts the learning information about the learning process. In this particular case, this memory of learning rates for the neural network's parameterization of the task. And the idea is that if you transfer this memory of learning rates, you learn to do better in the subsequent task. So for standard gradient descent optimization, H is typically a constant, a hyperparameter that you tune using hyperparameter search. With meta-learning, you actually parameterize H as a function of the gradient of the loss, parameterized with parameter theta, and you learn to map from the task loss to the learning rate. And the idea is that you do gradient descent few gradient descent steps on subsequent tasks. So in conclusion, I've shown how machine learning can be useful for robot control. And I've also explored cases where machine learning is limited. And I've discussed some research that is currently being done to address some of these limitations, which is transfer learning, integrating domain knowledge, sim-to-real transfer, and meta-learning. And with that, I thank you.
All right, questions?
We have these slides.
Yeah, we'll figure out how to get them to you.